Oh, okay.
Okay, so
So, Panrui, can you share your slide?
okay, let me share my screen. Uh, uh, okay, okay. So now can you see my screen?
Mm, yes, but it's quite slow.
Oh,
Can you make it bigger?
uh, how to make it bigger?
Maybe it's,
Yes.
yeah.
Uh, uh,
No, this is fine. Yeah.
yeah, yeah.
Okay.
Okay,
All right. So it's great um, to have a Panrui Ni for today's online seminar. Okay. So he's now a postdoc of University of Tokyo and working on homogenization problem for Hamilton-Jacobi. Okay, the title of his talk is Quantitative Homogenization of Convex Hamilton-Jacobi Equations with U over epsilon periodic Hamiltonians. Okay, please.
okay. Thank you very much for the introduction and the invitation. Okay, today I want to talk about this very recent work joined with Professor Mitake and Professor Chen. And it is the outline of this talk. So, uh, so in this talk, I want to consider this kind of equation. And here we have the term u epsilon over epsilon, and the u epsilon is the unknown function. So this term is important in our work, and this term also causes difficulties. And we consider the initial data to be globally Lipschitz in Rn. And we assume that the Hamiltonian H is periodic in the first and second variable, and is globally Lipschitz continuous in the second variable. And we assume that air is superlinear and convex in the last variable. And here the convexity is important since we will use the optimal control formula for the viscosity solutions. And we aim to show that the optimal convergence rate is O epsilon of U epsilon as epsilon tends to 0. Okay, the first difficulty is the equation 1 is not monotone in the unknown function u epsilon. So we cannot apply the comparison principle directly to prove that the solution u epsilon is equi-Lipschitz continuous. And in fact, we can prove that uh, the partial derivative of u epsilon with respect to t will blow up as epsilon tends to 0. And the second difficulty is the cell problem is defined on this non-compact space instead of n-dimensional torus. So actually, we it's hard to prove the boundedness of characters. To prove the convergence result in the homogenization problem, we usually need bounded characters. So here I write down the corresponding cell problem. And as you can see here, we have to find a constant h bar p for each fixed p in Rn. Then we have to solve this equation on Rn times 0 to the infinity, and we found to find a bounded solution of this equation. Okay, so here I also want to note that if we consider this Hamilton-Jacobi equation, which depends Lipschitz continuously on the unknown function u epsilon, which we usually call it contact type Hamilton-Jacobi equation, we have the normal cell problem. That is, we for each constant c in R and each fixed p in Rn, we solve this equation on the n-dimensional torus. And we can do this because we can use the vanishing discount method. Okay, so this problem is relatively easier to solve. And here we do not require that the Hamiltonian is periodic in the second variable. And this problem is actually completely solved by this work joined with Professor Mitake. And we gave the converse rate is O square root of epsilon. And now I want to give the derivation of our main equation. So equation 1 appears when we study dislocation dynamics. So dislocations are thought as line defects in crystals. So usually in crystals, we have a periodic structure. That is why our main equation 1 depends periodically on the unknown function. And we use the level set approach to describe dislocation lines. That is, we first take integer g and we consider this level set and we sort it as a dislocation line. So here is the figure of these dislocation lines, and these dislocation lines are indexed by several integers 1, 2, 3, 4, 5. And this picture was given by this work. Okay, so in real life, dislocation lines are affected by several obstacles, and these obstacles can be described by a scalar function, which is periodic, c x over epsilon. And moreover, dislocations can interact with each other. And it can be described by the so-called pitch corner force. And here is a picture of this force. And each dislocation line are described by a point, and we have this potential, and this potential describes the pitch corner force, and we can see here dislocation lines interact with each other. So then we can write down the corresponding level set equation, and the blue part corresponding to the obstacles, and the red part corresponding to the interaction, that is a pitch corner force. But here, G is a kernel that depends on physical quantities, and E is a step function which is discontinuous. So this equation is actually a discontinuous equation. And we have to first approximate the function E by a smooth function to get a continuous equation. And then, so this equation is actually a non-local equation because we have this convolution, and then we should take the homogeneous kernel, that is the kernel equals 1, and then we get a local equation. But it is not enough to get the real Poisson's of this equation, because this equation is not globally Lipschitz continuous in the unknown function. So we may have several discontinuous solutions. So we need to modify this equation, and following this work by Embot-Mono-Roy, we can finally do this modification, and we can check that the Hamiltonian we get satisfy all our assumptions before. So here is our main result. And firstly, we give a representation formula of U epsilon by the implicit variational principle of contact Hamiltonian systems. And using this representation formula, we can get the optimal converse rate of epsilon of U epsilon. And the most important thing is this rate is independent of time t. Then we can use this to some further applications. And moreover, under our setting, we can prove that the effective Hamiltonian is superlinear, convex, and therefore locally Lipschitz continuous. And in fact, to prove the Lipschitz continuity of the effective Hamiltonian is actually not easy to prove it directly if we do not use our converged rate result. And then we prove a weak analog of the in-soup formula for the effective Hamiltonian. and then use the convergence rate, which is independent of time t, we get the existence of bounded continuous characters. And we further assume that the Hamiltonian edge has a polynomial growth in the last variable, the momentum. We prove that the global Holder estimate of both the solution U epsilon and characters. Then since we get bounded continuous characters and we get the global Holder estimate of the characters, then we pass to the limit, we can get a global character. That is for all time t belongs to R. And to prove the convergence rate O epsilon, we use two main techniques. The first is the implicit variational principle, and the other is a curve theory argument by Professor Chen and Professor Yu. But different from their argument, we actually need to add another direction, the direction for the unknown function, and we cut curves in YR space instead of Y space. Before the proof, I want to first recall some references in dislocation dynamics. The first paper was given by Mono, and they assume that there exists a gamma zero such that we have this Lipschitz condition on the Hamiltonian edge. And the second one is important, and it's actually quite different from our setting because we assume that H is superlinear in P, but here they assume that the derivative of H with respect to P is uniformly bounded. So our setting is quite different from their setting, and they use the sliding method to prove the periodicity of modified characters. This is actually not the real characters because they first modify the Hamiltonian and then pass the limit. They are only able to get bounded semi-continuous sub and super characters, but it is enough to get the convergence result. And then Bells give another proof of the convergence result based on the level set approach. And then in this work, the authors give a convergence rate, which is epsilon to the power of 1/3. And here we can see that this rate is actually depends on time, capital T. And then I want to give some references about the contact Hamiltonian systems. First is the implicit variational principle, which was established by this first paper. And in this paper, they assume that the Hamiltonian is of class C3, and the special variable y belongs to a compact manifold with a boundary that is a closed manifold. And then they use this implicit variational principle to study Hamilton-Jacobi equations. And then they generalize the assumptions that is H is smooth and to the continuous setting that is continuous. And still, they assume that the special variable y belongs to a closed manifold, let's say in a n-dimensional torus. And actually, my work joined with Professor Wang and Professor Yan. We actually studied the Hamilton-Jacobi equation that depends periodically on the unknown function. But our argument is based on these three papers. So actually, we cannot apply the argument in this paper directly to our current setting here. Unless the initial data is periodic in Y. Okay. And there is another equivalent variational principle, which is called the Huglo's variation principle. And in this variational principle, we first consider this ODE, which depends on a curve C. And here R is a Lagrangian corresponding to the Hamiltonian. Then we can check that the Lagrangian is periodic in the first two variables, and globally Lipschitz in the second variable, and superlinear and convex in the last variable. Okay, so by since Lagrangian is globally Lipschitz in the second variable, by the basic theory of ODE, we can get a unique solution UC for this ODE and for fixed curve C. And then we put this solution into the following minimizing problem, and we want to minimize this action among all absolutely continuous curves that connecting to fixed points. Okay, and this variational principle was established by this paper, and they assume that the special variable belongs to Rn, but the Lagrangian is strictly convex in V. And in our setting, we only assume that R is convex, so we cannot apply their result directly to our setting. Okay, and then we actually will not use the Hercules variational principle, but we will use the idea of it. And then I want to mention about some references about the quantitative homogenization of convex Hamiltonian Jacobi equations. The first paper was given by Professor Mitake, Professor Chen, and Professor Yu, and they can prove this lower bound in a general assumptions, but for the upper bound, they have to add some further assumptions. And later, by the curve surgery argument, Professor Chen and Yu finally gave the optimal converse rate in this paper. And then there are several developments in this direction. And for the non-convex setting, this work give the convex rate to one epsilon to the power 1/3, and it is still a big open problem that can we get a better converse rate for the non-convex Hamilton-Jacobi equation. Okay, so let's start the proof. And first of all, we should establish the corresponding implicit variational principle under our assumptions. So here, R is periodic in the first two variables, and convex and superlinear in the last variable. And we actually prove that there exists a unique continuous function, M, which is called the action function or fundamental solutions. And we can get this kind of variational principle, this equality. And why we call it implicitly variational principle? Because here we can see the fundamental solution M appears on both sides of this equality, and we minimize this problem among all absolutely continuous curves that connecting to fixed point y and x. Okay, and moreover, we prove that there exists a minimizer gamma of this fundamental solution. And then we get this representation formula of the solution U epsilon by the fundamental solution M. And to prove this representation formula, actually we first applying a rescaling of the curves, and then we apply the rescaling of the value function, and then we can by some not very hard calculation, we can prove this representation formula. And moreover, we can prove that there exists a big constant M0, which depends on h and the norm of d phi, such that the minimizing point y of U epsilon satisfies this inequality. That is, the distance between x and y is bounded by M0t. Okay, so that is the main reason the converse rate we get depends on edge and norm of d phi. Okay, to prove this estimate, we actually use the fact that the Lagrangian is periodic in the second variable, and we also need to use that the Lagrangian is superlinear in the last variable.
Hi, Panrui. I think at this point, maybe people really forgot about the equation one already. Can you remind people and then explain
Okay.
why this formula is true before moving on? Thank you.
Okay. So equation one is ut epsilon plus h x over epsilon u epsilon over epsilon du epsilon equals 0. And we have a initial condition phi x. So here is our equation one. And so to prove this estimate, we have to use the fact that we first take the minimizer of u epsilon, and we have this equality and epsilon u epsilon over epsilon and gamma dot ds, and by using the superlinearity of air, and since air is Lipschitz in the second variable and periodic in the second variable, we actually have this we have this equality minus some constant one, which depends on the norm of d phi, and the capital K, which is a Lipschitz constant of the Lagrangian in the second variable. Okay, and we have this this equality, and at the same time we take a curve that equals x identically. Then we get the other direction, that is what, so here is gamma 0, and we get gamma phi x plus 0 to t air x epsilon 0 0 ds plus capital K times t, and we combine these two inequality, and we use the fact that phi is Lipschitz continuous, and we can get this estimate. Okay. And then to get the convergence rate of epsilon, we need to first prove the subadditivity. So for first, we take a large constant m0, and we prove that there exists a constant c which depends on this m0, such that this inequality holds. And actually, this m0 is arbitrary, and then we will take the m0 to be the constant given in this lemma. And to prove this inequality, we need to construct a curve by the definition of fundamental solution. We need to construct a curve that connecting 0 and sigma plus air y in time sigma plus air t. Okay, by the minimizer of these two fundamental solution. And to prove it, without any loss of generality, we assume that sigma t is bigger than 1. And we first take a minimizer gamma sigma of m sigma t0 sigma y sigma c, and we define this curve c sigma 1 as the value of this fundamental solution along its minimizer gamma sigma. And then we can easily prove that this curve satisfies this ODE. And this ODE is actually appears in the Hoglo's variational principle. And similarly, we define this curve CL1 as the value along the fundamental solution along the minimizer. And then we want to construct a admissible pairs that is a pairs connecting 0 and sigma plus Ly in time sigma plus Lt. So how to construct it? We first, since air is periodic in so here is y v, and so air is periodic in the first variable. Then we first shift the minimizer gamma sigma periodically to gamma k, and then we need to shift it and make sure that this endpoint and this starting point, the distance between them are bounded. So we can always do this because air is periodic in y. And then we can check that this starting point and this and the sigma plus Ly is also bounded if we shift it in this way. And then we just connect these points by straight lines alpha 1 and alpha 2. Okay, and then we get a curve, but this curve will take more time from sigma plus Ly to 0 because we add two straight lines. So we need to save time. Actually, because the action of gamma sigma is bounded from above, so we can find 2 points in the image of gamma k, and these 2 points, the distance between these 2 points is bounded independent of t. And then we can just connect these 2 points by a straight line alpha d with less time. And then we can save time and to make sure that the curve we get actually connect the sigma plus Ly to 0 in time sigma plus Lt. So this is the construction of the admissible pairs of this fundamental solution. And it is not the finish of the proof because we need to take care of the direction for the unknown function. Okay, so we first consider C2 is the solution of this ODE corresponding to the curve we constructed before with the initial data sigma plus LC. And we need to first take two parts of C sigma 1, which is marked in red and in blue. And since air is periodic in the second variable, so we can shift it periodically to the to the above the figure of C2, and then we can control this part of C2, the increment of this part of C2, that is this part, by the increment of this right line, because this part cannot increase rapidly because it cannot go beyond this right line. Otherwise, we have this intersect point, and it contradicts the uniqueness of solution of ODE. So this is actually by the comparison principle of ODE. So we can control the increment of this part by the right line. And similarly, we can control this part by the blue line. And finally, we can control this part, increment of this part by CL1 plus some integer n1. Okay, here n1, n2, n3 are integers, and then we are done, because we can add the increments of these three parts together, and we get this inequality, that is C2 L plus L sigma plus LT is smaller than C1 sigma T plus C1 LT, and plus some constant C. See, here we have a constant C because we have this discontinuous points. Okay, and we can prove that the differences between these discontinuous points are actually bounded, because it corresponding to the straight line we constructed here. And actually the distance between these points are bounded, so the speed of this straight line are bounded. So actually we can prove that these differences between these discontinuous points are bounded. That's why we have this constant C here. Okay, and then actually we will use the idea of Hooke-Law's variational principle, because the curve eta s we constructed before may not be the minimizer of Hooke-Law's variational principle. So we actually have m sigma plus lt 0 sigma plus ly sigma plus lc. This fundamental solution is actually no larger than C2 sigma plus LT. Okay, this is according to the Hooke-Law's variational principle. And these two terms are exactly these two fundamental solutions, because we define this curve, the value of these fundamental solutions alone is minimizers. Okay, so then we finish the proof of subadditivity. And once we prove that we have a subadditivity, we can use the Ficata lemma to get the convergence of this fundamental solution to some function m bar. And then we can define this value function by the limit m bar. And then we can think it as the limit of u epsilon. But to prove that the converse rate of u epsilon to this value function u xt is o epsilon is not enough. So we need to prove the subadditivity. And the subadditivity is shown below. So we first fix a large constant m0, and we for each t bigger than 1, and each y belongs to this ball centered at 0, we prove that there exists a big constant c depending on m0, such that this inequality holds. So how to prove this superadditivity? It is quite similar to the argument which I showed before. So we need to construct an admissible pairs of MT0YC, that is this fundamental solution on the left-hand side. And to construct this admissible pairs from a minimizer gamma of the fundamental solution on the right-hand side. Okay. And again, we define WS as the value of this fundamental solution alone is a minimizer gamma. And the important part is we should use the Bragg's cutting lemma, which is proved by a kind of fixed point theorem. We can show that we can take a collection of disjoint intervals, and the number of these disjoint intervals are bounded, and the bound is depends on n, only depends on n, such that we have this this property. So the sum of these increments are just 1/2 of 2y 2t and w 2t minus 2c. So this is 1/2. And then we consider a periodic shift of these pieces to gamma tilde w tilde. So here is the picture of the construction of the admissible path eta. So first of all, we take a collection of disjoint parts of gamma, which is marked in blue, and we shift it periodically. And we shift it in a certain way to make sure that the end point and the starting point and end point and start point and end point. So this point are the distance between this point are bounded. So we can always do this because air is periodic in the spatial variable y. Okay, so we shift it in this way, and similar as before, we need to save time to make sure that this path actually connect the point y and the point 0 in time t. Okay, so again, by a similar argument, because the action of gamma is bounded from above, we can actually find the 2 points in the image of gamma, and the distance between these 2 points are bounded independent of t. Then we shift it, and these 2 points is here, and the distance between these 2 points are still bounded since we shift it in a certain way, and we just connected by a straight line alpha d, and with less time. So we save time, and we make sure that the curve we constructed actually connect the y and 0 in time t. Okay, so this is the figure of the admissible path eta we constructed. And then, similar as before, we consider the solution of the ODE corresponding to the curve eta we constructed before. And similar to the proof of the subadditivity, we can control the increment of each pieces of the solution here, the solution of this ODE, by the pieces of omega ws to get this inequality. Okay, the first inequality holds still because of the Herclau's variational principle. And the second inequality holds because we control the increment of each pieces of V by W. So we have this inequality with constancy. And then this equality holds because we use the Burgos-Cutting lemma, so we have this 1/2 relation. Okay, so we have this equality, and by definition of W, it is exactly 1/2 of this fundamental solution. So then we conclude the superadditivity. So here is the figure of the argument. First of all, we take several disjoint collection parts of W, which is the value of the fundamental solution alone is minimizer gamma. Okay, and we shift it periodically above the curve V, and we control this part, the increment of this part by the right lines. Okay, and then we add them up to get this inequality with a constant, because we have this discontinuous point, and actually is corresponding to these 3 lines we constructed here. So we can prove that the differences at these discontinuous points are actually bounded, and the number of these discontinuous points are actually bounded, which is given by the Broca's cutting lemma. So we add them up, and then we finally get a big constant here. Okay, and this is the proof of subadditivity. And use subadditivity and superadditivity, we can actually prove that the difference between epsilon m t over epsilon, x over epsilon, y over epsilon, c over epsilon, and m bar is actually bounded by c times epsilon. This is because we first, for example, by the superadditivity, we have 2mt0 minus c smaller than 2t0 2y 2c plus c minus c. And we interact this inequality k times, then we get to the power km t0 y c minus capital C smaller than m 2 to the power k t0 to the power ky c minus c, and we divide this inequality by 2 to the power k on both sides, and we get m t0 y c minus c is smaller than m 2 k t0 to y plus minus c over 2 to the k, and we send k to infinity. And actually, we know that the limit of this fundamental solution is m bar. So actually, we send the k to infinity, and we have t0 y c minus c is smaller than m bar. t0 y c for every t. So we take t y c to be t over epsilon, y over epsilon, c over epsilon, and we times epsilon on both sides of this inequality. And we use the fact that the m bar is one homogeneous because it is the limit of this fundamental solution. So it is actually equal to m bar t0 yc. And then we can get the difference of this we can get the one side of this equality. And similarly, we use the subadditivity to give the other direction of this estimate, and then we can prove that actually we have this estimate. And then we use the representation formula of u epsilon by the fundamental solution m. We can finally get the convergence rate or epsilon of u epsilon. Okay. So then we finish the proof of the convergence rate of epsilon, and we can use this fact to get the existence of bounded characters. So we first fixed a p in Rn, and we consider the initial data W0, which belongs to bounded uniformly continuous function and globally Lipschitz continuous function. And we consider this equation, and we can prove that there exists a constant c, big constant c, depends only on edge and the norm of the initial data W0 and p, such that we have this bounded term. And actually, we can easily check that this term is satisfies the corresponding zero problem. So this term is the bounded character we want to get. Okay, and the constant h bar p, which depends on p here, can be thought as the large time average of the solution W of this equation. Okay, and this constant h bar p can be thought as an analog of the rotation number of a homeomorphism on circle. So why I say this? Because if we add 1 in the initial data W0, and we can easily check that W plus 1, W plus 1, W plus 1 still solve this equation with the initial data W0 plus 1. Okay, and this structure is quite similar to the homeomorphism on circles. And as the discussion I showed before, we actually do this argument along curves instead of all y in Rn. Okay. And at last, I want to give the idea of the proof of a global Hölder estimate of U epsilon. Okay, so here we know that the convergence rate of U epsilon to the limit Ux is O epsilon, and this convergence rate is independent of T. And this is important. And also, the limit uxt has nice property that it grows linearly in time t with the slope h bar p. Okay, so we can easily prove that this term is bounded for every xy in Rn, and for every t bigger than 1, and for every epsilon belong to 0, 1. And then we want to estimate the difference between U epsilon y t and U epsilon xt. So how to estimate this difference? We need to take a minimizer of U epsilon xy xt gamma, and we have to construct an admissible path of U epsilon yt. That is an absolutely continuous curve that ends at the point y at the time t. Okay, so how to construct it? We just let this path equals the minimizer gamma from time 0 to time t minus tau, and here tau is a small constant which should be chosen later so that we can have the optimal Hölder estimate. So we just take the admissible path like this, and then we connect gamma t minus tau, these 2 points, and y by a straight line. Okay, and then we consider the difference between the action of the curve gamma and this admissible path, which is marked in red. And we only need to compare the action of this part and this part. Okay, and then we use the fact that we have the boundedness of this term, this difference, and then we can prove that actually the difference between this part of gamma and this straight line are bounded for all t bigger than 1 and for all epsilon. And then we can get the global Hölder estimate of U epsilon. And this similarly, we can get the Hölder estimate of the characters. Okay, and so here I also want to mention that if we can only get the local regularity of U epsilon, it make no sense, because for finite time, we can always get a Lipschitz estimate with this estimate. So we need to prove the regularity global in time. Okay. So at last, I want to mention some further discussion. First of all, I want to mention a conjecture given by Di Giorgi, which concerns the homogenization problem of linear transport equation. So as we know that the characteristics of a linear transport equation is a solution of a certain ODE. So we consider this ODE. This is corresponding to the homogenization problem of a linear transport equation. And here f is a periodic function. And if we can get the convergence rate of this ODE by the characteristic method, we can get the convergence rate of linear transport equation. And actually, if we consider the initial data in our main equation 1, that is this equation. And we just take the initial data phi equals constant. Then this equation reduces to an ODE. And we can use our result of, to get the convergence rate or epsilon of linear transport equation, and it actually solves this conjecture in one dimension. And secondly, I want to mention that the existence of effective Hamiltonian and the Lagrangian suggests a possible generalization of the Aubry-Masse theory, because in the original paper of Masse, he defined the alpha function and beta function, which is exactly the effective Hamiltonian and the effective Lagrangian. So here we have the effective Hamiltonian and effective Lagrangian, which depends only on the rotation vector in the special variable y space. So this suggests us to generalize the Aubry-Masse theory. And here edge is periodic in the first and second variable, and superlinear and convex in the last variable. So actually we can consider y r belongs to n plus 1 dimensional torus. Okay. And then I want to mention that can we get a PD argument for non-convex and non-local Hamilton-Jacobi equations that appears in the study of dislocation dynamics? So as I said before, the original equation we get is actually a non-local equation. So it is still unclear.
Mm-hmm.
Then I want to mention that can we get some result about the weakly coupled system of Hamilton-Jacobi equations similar to the form we studied here. So here we can only deal with a single Hamilton-Jacobi equation. And this problem might be hard because, as I said before, the effective Hamiltonian can be thought as an analog of a rotation number. And if we consider weakly coupled systems, it is actually in some sense equivalent to consider the existence of a uniform rotation number in higher dimension. But actually we cannot expect this because the lack of comparison principle in higher dimension. And at last, I want to mention that we can also consider this second-order Hamilton-Jacobi equation. And this problem can be thought as a generalization of this work. In this work, they consider the a homogenization problem with this term, u epsilon over epsilon, and the equation is independent of first and third variable, and they called it the semi-linear heat equation. Okay, this is all I want to talk today. Thank you very much.
Okay, great.
Okay.
Okay, so question time. So, is there somebody who want to ask a question, give a comment?
Thank you for a great talk. Can I ask two questions?
Okay.
The first one may be very subtle, and so you mentioned that you obtained the optimal path by solving the ODE via M. I was wondering, so for the fundamental solution M, it might be not very regular when at the origin. How can you what happens? How can you still solve the ODE?
Sorry, which part?
I think you just mentioned it by one sentence. You mentioned that to obtain an optimal path, you solved an ODE via M, right?
So when ODE while M.
So
You,
so you need the optimal path, right? And you told us like you solve the optimal path by solving an ODE involving M, involving the fundamental solution.
You mean this equation?
no,
This ODE?
Andrew, you come to your definition of M.
Definition of M is okay.
Yeah,
Okay. Here.
yeah, here.
Okay.
Yeah. My question is about this minimizer gamma.
Okay.
So I remember you told us that you can get this minimizer by solving some ODE that involves M itself.
Yeah.
And but M is not very regular when say T, X, and Y they are close to zero. So I'm wondering how can you how
Yes.
you
Yeah.
find the minimizer?
This is reason we cannot set the time t equals 0. So we have this. So actually, yeah, for each t bigger than 1 and for each fixed x and y, we can find that this fundamental solution is actually finite valued.
Okay, my question is about can you tell me like more details, like how do you find the minimizer gamma?
Okay, so in our argument, we first consider this M1 TXY C, which is C plus the infimema of T air, and in air we first take 0 here. So this is the classical variational principle. Okay, and we get M1, and we put M1 into air again. C plus infimum of. This is like a Picard sequence. And here M1 is Lipschitz continuous. So we put it in air. And again, we can get the existence of minimizer of M2. And then
one is do you mean locally Lipschitz or is
locally Lipschitz for time t
positive time?
positive, yeah.
Yeah, I think we can discuss this one more because this is the implicit variation principle is actually one of the key point here.
Yeah.
The post question is after you prove the existence of M, you can prove that there exists a minimizer, but there's not a lot of regularity, Paul. I mean, the minimizer doesn't have a lot of regularity.
Yeah, it's a absolutely continuous curve because it depends on S. So M depends on S, so we have S here.
But there does exist a minimizer. My question is about the existence. Okay.
I mean, because L is still super linear, so I mean, and convex. So the existence of minimizer should be fine, Paul. It's more about, whether your minimizer has certain regularity.
Yeah. So once we prove that this exists a continuous function m, and we put m here, and then we can get the minimizer. But we do not know the regularity of the minimizer, because m actually depends on s.
Yeah. So
okay.
for Lagrangian, depending on time, you still have existence of a minimizer under some grow and convex assumption.
Yeah.
But whether you have that is regular enough and some regularity of gamma, that's a different issue.
I got you. Thank you. And another question may also be a little bit technical. Can you go to page 26?
Okay. 26, 20. Here. Okay.
Yeah, I don't get how do you use the boundedness of u epsilon xt minus u epsilon y t minus 1. How do you use that at the end of the step?
Yeah.
Yeah, please.
Okay. So actually we use the value of u epsilon x t, and u epsilon, actually we take y to be gamma t minus tau t minus tau here, and tau is smaller than 1. So this is actually the integral of air gamma dot, and this is the action of no, t minus tau. So this is actually the action of gamma in this part. Okay, and for the action of this straight line, we just use the triangle inequality. And to say that actually, if we know that the action between gamma t minus tau and x is bounded, then we use the triangle inequality, and we know that the distance between x and y is given. So the action of this straight line can be bounded.
Well, yeah, that's my confusion, I guess, because you need something to you need it to be small, right? But because x y are close, and
Yeah.
you need the cost there to be small, but you only have boundedness at hand. How do you go from boundedness to something very small?
Yeah, so actually we need to take tau. Tau is the distance to the power some alpha.
Yeah, but no matter how small tau is, your the left-hand side of what you wrote is just bounded. It is because I mean I don't get you, because you use that u epsilon xt minus u epsilon yt minus 1. You use boundedness of this guy. It is not supposed to be small. That's why I'm confused how you use that in your proof.
You mean this
Yeah,
term?
what he meant is that how do you go from boundedness to something of holder, to something?
Yeah.
Yeah,
Yeah.
so here we need to add some further assumptions on the growth of air. So air has a polynomial growth in gamma dot, and then we can use some inequalities, such that like the Jason inequality to get so we have some gamma dot to the power, and we can get some some power.
Maybe can
Okay.
you show Paul the actual calculation in the paper? Can you share the paper? I think it's a great point to show.
It's okay. You can also just point out to me the page. I'll read it myself.
Or maybe
Okay.
we can keep it for the informal discussion.
Yeah, I
How
think
about that?
that's
Okay.
better.
Okay. Thank you so much.
Okay. So here, I mean the important thing is we need to add the further assumption on air, then we can get some further estimate for the distance between x and
Okay.
gamma. Yeah.
Okay, thank you.
Okay.
Any other question, comment? Okay, if not, let's thanks Panrui once again.
Okay.
Thank you.
Okay, so can you stop the lecture?